and welcome to the second video accompanying Chapter 3 of our astronomy textbook. Okay, so in the second video, we're just going to cover a single section. It'll be a shorter video than the first one, and we're just covering section 3.3 with the title, The Fact and Theory of Gravity. So you may wonder about that funny title. Why is it the fact and theory of gravity? Well, because when we say the fact of gravity, we're talking about the law of gravity. And a law is a term in science that refers to a simple observation that has never been disproven. Gravity is the idea that mass attracts mass, which means you fall downwards on the surface of Earth because you're attracted to Earth. That's a law. Okay? Now explaining why that happens and the exact form of how it happens numerically, that's a theory. Okay? So that's the difference between the two. Okay? So let's get into it. So first of all, in order to talk about gravity, we're going to do a quick summary of some other physical terms. All right, so what are they? All right, so we have speed. Okay, well, speed is distance per time, or change in position per time. Okay, so distance per time. The units would be meters per second, because distance is measured in meters, time in seconds. Okay, example, 10 meters per second. Okay, that's speed. On the other hand, there's something called velocity. Velocity is speed with direction. Example, 10 meters per second due east. So if you define the direction, you've upgraded the speed to a velocity. You've made it a more sophisticated expression. Okay? Acceleration is the rate of change in velocity. Okay? So it's speed per time. So since speed is meters per second per second is meters per second squared. So that's the units of acceleration. All right. So I want to circle back around and quickly say the difference between speed and velocity. If you had a car that was going 60 kilometers per hour and it was going in a straight line, then it's not accelerating. However, if you have a car that's going 60 kilometers per hour but is turning, like the picture here, since the velocity is changing because the direction is changing, there actually is an acceleration. So the very act of turning requires an acceleration, all right? Even if your speed maintains a constant value, because your velocity does not, because the direction changed, okay? That's the biggest idea that trips people up, okay? So what about acceleration of gravity, right? Because we defined speed, velocity, and acceleration. That's going to segue into discussing gravity and forces, okay? So all falling objects accelerate at the same rate, okay? And this is ignoring friction, all right? So, it's not that significant for large objects. We don't worry about it in astronomy, so we're going to ignore friction. The acceleration on Earth is about 10 meters per second squared. So that means that speed increases at a rate of 10 meters per second for each second of falling. So if I drop something off the edge of a building, at first it's at rest. So at t equals 0, the velocity is 0 because you just dropped it. You didn't throw it down. After free fall for 1 second, it's sped up to 10 meters per second. After it's been in free fall for 2 seconds, it's sped up to 20 meters per second. If it was in free fall for 3 seconds, it'd be 30 meters per second. So it speeds up at that rate. Okay? That's a constant acceleration. So that means you always expect the same change in velocity every subsequent second. Okay. So Galileo showed that G, remember Galileo when we talked about the history of the foundations of astronomy? That G is the same for all falling objects, regardless of their mass. So gravitational acceleration is universal on the surface of Earth. Okay. Why is that? Well, we'll come back around to it. Okay? So, a couple other things to define. Momentum is an important term in physics and astronomy, and it's simply mass times velocity. We already defined velocity, meters per second. Mass is measured in kilograms. So that means momentum is just kilogram meters per second. Okay? And the reason we would come up with that particular combination of mass times velocity is because momentum is conserved. If you have a collision or certain events, certainly like things like in astronomy, planets crashing together, or just the very idea of dust swirling around in space, momentum must be conserved. Okay? But what about force? Okay, well, a force creates a change in momentum. So we have a nice segue, right, from momentum to force. And specifically, a net force changes momentum, which generally means an acceleration, a change in velocity. Okay, so if you have a net force that isn't zero, so if you push on something and there's no equal pushback, then the momentum will change. All I'm saying is, like, imagine an object. You apply a pushing force to it. That object that was at rest starts to move, which means it accelerated because you applied a force. Okay? You changed its momentum. There's also something called angular momentum. And angular momentum is all about this idea of rotation. So momentum is all about moving in straight lines. Angular momentum is very relevant to astronomy, actually more than translational momentum, more than standard momentum. And angular momentum is about rotation, like a spinning planet, or orbit, all the way around something. Okay, both of those would have angular momentum, both types of rotational motion. Okay, it is also conserved, and it can also be created by forces. So you can change angular momentum with an outside force having an effect on that motion. So for each of the following, is there a net force on the object described? Okay, so remember, net forces create acceleration, they change momentum. Look at your options. Okay, so you're going to answer yes or no for each of them. So you have to come up with five yes or no's. Okay, have you come up with all of them? Pause if you need to. Okay, so a car coming to a stop, definitely, because it slowed down, it changed velocity. A bus speeding up, yep. An elevator moving at constant speed, no, because there's no change in direction or speed. A bicycle going around a curve, yep, because even if it maintains constant speed, the curve implies there has to be a force. A moon orbiting Jupiter, yep. So that's interesting. So a moon, which isn't speeding up or slowing down, still requires a force because it's constantly turning. It's taking a circular path or an elliptical path around the planet that it's orbiting. That requires a force. What force? The force of gravity. All right? So a couple more terms, mass and weight. So mass is a measure of the amount of matter in an object. Weight is the force that a scale exerts upon an object. Okay? So mass never changes no matter where you are in the universe. Weight is completely dependent on where you are in the universe. I weigh a different amount on Earth than I would on the moon because gravity is less on the moon than on Earth. All right? And furthermore, you're weightless in free fall. Okay? Because if you're in free fall, the floor that you're standing on and the scale on that floor is falling with you, so you can't push on the scale and the scale can't push back. So there would be no weight reading. You are weightless. So on the moon, my weight is the same, my mass is less, my weight is less, my mass is the same. Which is the correct answer? I just said it. Okay? Do you see it? Your weight is less, but your mass is unchanged. Okay? So, why are astronauts weightless in space? Okay? Well, the idea is because they're in free fall. Okay? That's what orbit is. It's free fall. Now, why is that? Well, let's think about an example. An imaginary giant tower that we've built someplace on Earth. If I was to jump out of that tower at some high speed, I'd take an arc path coming down. If I jumped out at an even higher speed, I'd take a larger arc. But if you jump with enough speed, the arc of your downward fall matches the curvature of Earth. Thus, you never hit the ground. And that is exactly what a satellite is, artificial or otherwise. All right? It is just an object that has a great enough velocity that as it falls, as it gets pulled back to the Earth, it misses the Earth because the Earth curves away underneath it. Okay? All right, so it's in a constant state of free fall. All right, more about angular momentum. It describes objects that are spinning or moving in circles, as I said. Now, the type of force that applies to angular momentum is called torque. It's actually not a force. It has slightly different units, but we can think of it as being very similar to a force. So a net force changes momentum. A net torque changes angular momentum. And here are the two examples of angular momentum: orbital angular momentum and rotational angular momentum. All right? And a net torque could change that. Now, is there a net torque that's going to come into our solar system and disrupt our orbit? Probably not. But if some giant object came flying through our solar system, it could exert a large enough gravitational force and an associated gravitational torque that could disrupt either our orbital angular momentum, our rotational angular momentum, or both. Okay? So if that doesn't happen. All right, so how do we describe motion? So in summary, we have speed is distance per time. All right, velocity is speed with direction. A change in velocity is called an acceleration. Momentum is simply mass times velocity, and forces change momentum, thus producing an acceleration. Okay, how is mass different from weight? Mass is a quantity of matter. Weight is specific of the force that's acting on that matter. Objects are weightless in free fall, and orbit is a form of free fall. Okay, so how does this all tie into Newton's laws of motion and gravity? Okay, well, let's see. Okay, so here is Newton. Okay, one of the big historical figures we haven't mentioned so far, right? Because we went from Copernicus to Tycho Brahe to Kepler, and then mentioned the importance of Galileo in supporting the Copernican model that had really kind of gained credence from Kepler's three laws. But Newton came later. If you look at the year, it's 1642 to 1727. Essentially, Newton was born the year that Galileo died, right? And remember, Galileo was a contemporary of Kepler, all right? So we kind of have the next saga in this early foundational era of astronomy and physics. And what Newton did is he built on the ideas of Galileo, namely the idea of inertia, and came up with three laws to summarize all of motion. Okay? Now, in addition to his three laws of motion, he came up with a law of gravity as well. So you can think of that as Newton's fourth law, but it's never called that. It's always just called Newton's law of gravity. Okay? He also did a lot of other things. He made some huge breakthroughs of light and telescopes, and he also invented calculus. Okay? But here we're mostly interested in his laws of motion and his law of gravity. All right, so Newton's first law of motion is his rewording or refinement of Galileo's concept of inertia. And that's the idea that objects will stay in motion unless they're acted on by an outside push or pull. All right, and if you recall, and there's a lot of pieces to this puzzle, that the importance of Galileo's law of inertia was that it kind of rectified or ameliorated the concern that Earth couldn't be in motion, because if Earth was in motion, why aren't we getting thrown off of Earth? Well, that's because we, as people that have mass, right, have our own inertia, so we just stay in motion with Earth if there's no external force acting on us. So sure, we're flying through space at thousands of kilometers per second, but we have inertia, so we just continue along. Okay? So, Newton's first law of motion. An object moves at constant velocity unless a net force acts to change its speed or direction. So great examples of that are spacecraft. If you push a spacecraft out into deep space, it'll just continue moving forever until a force acts on it. But if it's far away from other planets, then there's really no significant forces that act on it, so it can just continue forever. No fuel is required. It will just coast forever. Because one thing that makes us think that objects eventually come to rest is the idea of friction, air resistance, these things that are just part of living on Earth surrounded by an atmosphere. That's great, we can breathe it, but it means everything gets slowed down. There's always something to stop motion, but not so in the vacuum of space. Okay? What about Newton's second law of motion? Well, there are two equivalent ways to express the second law. The first is that force is mass times acceleration, kind of a direct tie-in to the slides we were just looking at. So the law is simply F equals ma. So in other words, if you have bigger force at a particular mass, then you have a bigger acceleration. So if F goes up, A goes up. Or if you keep F the same, but you make A bigger, then acceleration must compensate by going down. Right? So that's all the law says. All right? However, there's another form of the law, because remember, there's a direct relationship between momentum, acceleration, and force, and that says that force is actually a rate of change momentum. So it's momentum per time. So it's change in momentum per change in time. And that would be force. Okay? And this form, although it's less well known to an introductory student of physics or astronomy, is actually the way it was initially written by Newton. Okay? And remember, momentum is just mass times velocity. Okay? Now the third law. Okay? So the third law, often known as the law of force pairs or the law of equal and opposite reaction forces, says that for every force, there's always an equal and opposite reaction force. So if I push on something, that something pushes back. All right, great example. A rocket is propelled upward by a force equal and opposite to the force which gas is expelled out its back, right, through the nozzle of its rockets. Now, you might be like, oh, does that mean that the gas in the rocket have the same velocity? Well, certainly not. The gas is less massive, so its velocity is very large. The velocity of the rocket its mass is relatively large, so its velocity is smaller. All right? So because the forces are equal and opposite, but the velocities need not be. Okay? So how does the force that Earth exerts on you compare with the force you exert on it? Because right now you're being pulled down by Earth. Maybe you're sitting on something, so you're not in free fall, but you're still getting pulled down by Earth. Well, does that mean that you pull back up on Earth? Earth and you exert equal and opposite forces on each other. Every time you jump and get accelerated down to Earth, you are pulling up on Earth and accelerating it towards you. Is that right? Yeah. But the thing is that Earth is 10 to the 24 kilograms. So the acceleration of Earth is so infinitesimally small, you'd never be able to measure it. Okay? So yeah, it's true, you do actually pull the planet towards you, but in all practical purposes, you don't, because it's so small, because it is so much bigger. It is it is a trillion times more massive than a single human being. Okay? A compact car and a Mack truck have a head-on collision. Are the following true or false? So we're going to have 3 trues or false. All right? The force in the car on the truck is equal and opposite to the force on the truck on the car. Well, that's Newton's third law, right? Okay. The momentum transferred from the truck to the car is equal and opposite to the momentum transferred from the car to the truck. Okay, well, I said that momentum is conserved. Okay. The change in velocity of the car is the same as the change in velocity of the truck. What? That can't be right. Because when you see the two of them crash together, the car crumples up and the truck might just continue moving forward, whereas the car comes to a complete stop, reverses direction. So the car would have a much bigger change in velocity. All right? So it's true, false. How is that? That's because momentum is always conserved, the forces are always equal and opposite, but velocity is definitely not conserved. Because momentum is mass times velocity. So it's entirely possible for momentum to be conserved, for forces to be equal and opposite, but if the masses are different, the velocities will also be different. And that's very important. All right? So, in summary, we've seen the 3 laws of motion, all right? And we've seen what they are, okay? So, now Newton's 4th law, but again, we never call it that. We call it the Universal Law of Gravitation, or Newton's Law of Gravity, okay? And one big thing we're talking about is how it fits in with Kepler's laws, in particular Kepler's 3rd law. And we'll finally summarize this crash course in introductory physics, especially how it relates to astronomy. Okay, so here it is, the Universal Law of Gravitation. Okay, so the first part of the law says every mass attracts every other mass. So everything that has a mass is pulled to everything else. So if you're sitting in your room right now, all the little objects in your room are actually being pulled towards you. But you don't see them like flying off the shelves, right? You don't see objects coasting along tables getting pulled towards you. It's not like you're a giant magnet and all the metal objects in the room are getting sucked towards you. So how is that then? How is it true then that all mass attracts other mass? Well, it's because the force is tiny. Turns out the gravitational force is really small, especially compared to other forces like magnetic forces. Okay? So if it's such a small force, how is it that it's so important? Well, because when you have giant things like planets and stars, even though the force is so small, the mass is so large that it ends up being significant. And let's see how that works out mathematically. Okay? So, the attraction, that idea that all masses attract other mass, is directly proportional to the product of their masses. Okay, so the size of the force, the size of the attractive pull between any two masses is bigger if their masses are bigger. Okay. And you actually multiply the two masses together. Furthermore, the attraction is inversely proportional to the square of the distance between the centers of the two masses. Okay? So that just says, I know it sounds kind of complicated, but it just says that the further you are away from something, the less gravitational pull it exerts on you. So as you move away from Earth, you get less and less gravitational pull. Okay? So here's the formula. This is gravitational force, Fg. Okay? Big G is a constant of the universe. It's equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. The Newton is the unit of force. Okay, this is just mass 1 and mass 2. These are just both being kilograms. Okay, so both the masses are in kilograms. So you have a kilogram squared in the numerator. And then in the denominator is distance squared. And distance is just the distance between the two centers of the two things that are attracted. So in your case, if you wanted to calculate the gravitational pull on you from Earth, you would take the distance between your center and the center of Earth, which would just be the radius of the Earth, which is 6,370 kilometers. That would be your d. Convert it to meters and square it. Okay? And so that whole business together would be your gravitational force. Your mass times Earth's mass, radius of Earth squared, and then this particular constant. If you wonder where this constant comes from, no one quite knows, but it's been experimentally determined many, many times in physical experiments. Okay? Physicists suspect there's some particle that creates it, but they've never actually confirmed the existence of this particle. Okay? So, now, how does Newton's law of gravity, because this is it right here, in the circle, that's Newton's law of gravity, okay, in full equation form. But how does it apply to orbiting objects? Okay? Well, ellipses are not the only orbital paths. Orbits can be bound and unbound. Parabolas and hyperbolas are examples of unbound orbits. That's where you escape the gravitational pull. You have a great enough momentum that you escape the force. That external force is not large enough to actually cause your momentum to become an ellipse. Instead, you just continue away. Okay? All right. So that is the final summary of how this relates together and how you can imagine how gravity can create things like orbits. Okay. Thank you so much for watching the second video for Chapter 3, and stay tuned for Chapter 4 next week.